Hi, I'm David Barreton from the Department of Chemistry at Duke University, and I'd like to tell you a little bit about the polarizability of electrons in molecules with the idea of understanding the origin of the differences in the electrical conductivity of different kinds of molecules and different kinds of matter. So I have a simple demonstration to illustrate the idea of polarizability. So in this bottle I have a green liquid, and the bottle is half filled. If I tilt the bottle, the liquid inside feels gravitational forces and it moves around. So I would say that liquid polarizes as I move the bottle. Okay? Now it's important to notice that that liquid only moves around as a consequence of the bottle being half empty. Okay? If the bottle were full, the story would be different. So here's a bottle with a red liquid. I tilt the bottle, and you don't notice anything much happening to the liquid, right? That's because the bottle's filled. There's no place for the water to go, okay? The story is very similar with electrons and molecules. In order for electrons to polarize, to respond to being pushed by an electric field, say, they need space. They need space to move. And for electrons, that means having empty orbitals nearby. So let me draw a sketch for you. If I have electrons occupying a molecular orbital, like this, and there are no empty orbitals nearby, I can push as hard as I like on these electrons, and they're not going to go anywhere. But if I have empty molecular orbitals nearby, applying an electric field to the system will cause these molecular orbitals to mix with one another and the electrons to be able to move around, just like the water in this bottle was able to move around when I tilted it. Okay? So let's explore some of the reasons why the words I just said are sensible. So let's explore the molecular orbital situation that gives rise to polarizability in a material like a metal. Imagine that I have several atomic orbitals associated with a metal atom. It could be a gold or a silver atom. And each of these lines represents the energy of one of those atomic orbitals. If I let those atomic orbitals interact with one another, I'm going to give rise to a set of molecular orbitals. And those molecular orbitals will have a range of energies. And some of those molecular orbitals will be occupied with electrons, and others will be empty. So this is the analogy of my bottle being half filled. Electrons in a scenario like this can move very easily when I tilt the bottle or when I push on those electrons. Okay? On the other hand, imagine that I fill up this set of molecular orbitals completely with electrons like this. Okay. Now I'm in a scenario like I showed you with this bottle that's filled with water. I can push on these electrons with an electric field, and there's no place for them to go. They're stuck in their filled bottle. Okay. This scenario here corresponds to an insulator. The picture that I showed earlier of partly filled molecular orbitals corresponds to the situation we have, assuming the system gets large enough, corresponds to a metal. Now let's take these ideas and apply them to some simple organic compounds. So let's look at two simple organic compounds. Polyethylene, which is the material that holds your milk in milk bottles, and it looks like this. It's a polymer made out of carbon-carbon single bonds and so forth. It's a polymer that's made out of these repeating units. And let's compare this polyethylene to a conjugated organic material, polyacetylene. Okay, and now what I'd like to do is look at the underlying atomic orbital structure of these two species and understand why one of them gives rise to insulator-like behavior and the other to semiconductor or even metallic behavior. So let's look at the underlying atomic orbitals that exist on polyethylene. So these carbons that I've drawn here are sp3 hybridized. And so a cartoon version of the relevant hybridized atomic orbitals for this system, there's my second carbon, would look like this. I won't bother with the orbitals associated with the carbon-hydrogen bonds, but rather just with the orbitals associated with the linear hydrocarbon chain. These are sp3 hybridized orbitals, and they form sigma chemical bonds, sigma bonds. And so on down the chain, sigma bond here, and so on in that direction, and so on in that direction. And these are very strong bonds. And so the interactions here among these two hybridized atomic orbitals are very strong. And among these orbitals on the same carbons are very weak. There and there. Okay? And so the way I'd like to describe the chemical bonding in the system is to start by drawing sigma bonding orbitals associated with this carbon-carbon bond and sigma star orbitals. Now, I mentioned that these interactions are extremely strong, so this gap, this bonding, anti-bonding energy gap, is very large on the scale of 10 electron volts. Now, I mentioned that these interactions on the same carbon among the sp3 orbitals are very, very weak. So imagine your polymer as being built out of a bunch of sigma and sigma star orbitals of those repeating units. So there's the sigma, sigma star from this repeating unit. Now comes the next one from this repeating unit, and the next from that repeating unit, and so forth. And now we allow those carbon-carbon sigma and sigma star bonds to interact with one another. And what we'll find is a cluster of molecular orbitals down here, bonding orbitals, and these will all be occupied. And a bunch of anti-bonding orbitals located up here, very tightly packed in with one another, and those will all be empty. Okay? And so this situation is like having a filled bottle of electrons down here and very far away an empty bottle with no electrons in it. This system will be will have a relatively low polarizability as a consequence of that separation in energy of the bonding and anti-bonding molecular orbitals. And that low polarizability arises from this large gap between the filled and the empty states. Now let's look at polyacetylene. The molecular interactions that give rise to the polarizability and the conductivity in the system come from the pi electronic orbitals. So let's draw the sketch for polyacetylene that corresponds to the sketch I just made for polyethylene. Okay? So let's get rid of our sigma backbone. Okay? For now, and let's put pi electrons, p electrons on the carbons. Okay? And now these are the orbitals that give rise to the pi and the pi star bonding and anti-bonding interactions. Okay? Now let me draw one of these carbon-carbon double bonds and its neighboring repeating unit, which would have a carbon-carbon single bond. Now, the carbon-carbon double bond is a strong bond, but this neighboring bond is not so much weaker. So this is still strong. This interaction between these two carbons, between these two p orbitals, is strong, and this is pretty strong. Maybe 10 or 20 or even 30% weaker, but not that much weaker than the interaction associated with the double bond over to the left. As a consequence, this gap between the pi and the pi star states is smaller. So if I draw the corresponding diagram here, corresponding to the pi and to the pi star antibonding states, well, this gap is much smaller because the difference in the overlap between these p orbitals, this pair, and this pair is not very different. Okay? So what I will find in polyacetylene is a cluster of antibonding levels that comes much closer in height to the bonding levels. And so now I have a filled bottle of electrons and an empty bottle closer by in energy. And when I disturb this molecule with an electric field, these molecular orbitals will mix with one another, and the material will be more polarizable than in the case of polyethylene, where the separation energy was much larger. There's a little more to the story that I'd like to tell, and that is I can make this system more conducting still. I can make polyacetylene nearly as conducting as silver by removing electrons from some of these high-lying molecular orbitals, or by adding extra electrons to these empty molecular orbitals. And then that becomes more analogous to my first example of a partly filled bottle itself. This would be an example of a highly doped semiconductor, which becomes highly conducting, as opposed to the case where the electrons were present here and I had a semiconductor, a material with a smaller gap and a larger polarizability, say, than polyethylene, but not as large as I would have in the case of a metal. So understanding these basic principles, we have the tools at hand that we need to understand organic conducting materials, organic light-emitting diodes, organic solar cells, and many other phenomena that arise in nanoscience.